Hello Physics 1 students, and welcome to the Lab 12 Prelab video. Today we're going to be talking about energy conservation. So as you can probably see in this graphic, there's kind of an inverse relationship between potential energy and kinetic energy. So when potential energy is at a maximum, kinetic energy is going to be at a minimum, and the opposite is true. When kinetic energy is at a maximum, then potential energy is going to be at a minimum. So you can see over here on the left-hand side, this is where I have our potential energy information, and you can see when we are up at the top point of the motion, that's where your height is at a maximum, and you can see here for the formula for potential energy, it's equal to mass times gravity times height. So it should come as no surprise that our potential energy is at a maximum when our height is at a maximum. In a similar vein, that means that when our object is at the ground level, so at a height of 0 meters, that's when our potential energy is going to be at a minimum or equal to 0, right? Because anything times 0 is equal to 0. Regarding kinetic energy, we know from last week that kinetic energy is equal to 1/2 times the mass times the velocity squared. So in this case, when our velocity is at a maximum, which is right at the bounce here at ground level, that's where our kinetic energy is going to be at a maximum because that's where our velocity is at a maximum. The opposite is true up at the top of our motion, right? As we talked about as early as lab 2, up at the top of the motion, the velocity is equal to 0 meters per second. So that's where our kinetic energy is going to be at a minimum, or that's where it's going to be equal to 0, because anything times 0 is equal to 0. So the last thing I want to mention before we get into the pre-lab practice problems is that if the problem does not tell you any energy was lost at the bounce, you can assume that it wasn't. That means that our maximum potential energy is going to be equal to our maximum kinetic energy. And this is really handy because as you can see here, I filled in what the formula is for potential energy and what the formula is for kinetic energy. And so if you're given a problem where they don't tell you what the mass is, it's really handy to be able to cancel your masses and then either have to solve for your maximum height or your maximum velocity. Here you can see the masses are gone because they canceled from both sides. And so whether the problem is asking you what the maximum velocity is or what the maximum height is that the object reaches, this is a really handy equation for calculating either one of those. So those pretty much hit all the highlights for the things that are going to be really important and relevant for doing the pre-lab practice problems. So you can see here that there are going to be 8 pre-lab practice problems. So let's get started. All right, so in practice problem number 1, this relies on the prompt that says there's a 3-kilogram ball that rises 4 meters above the ground when it is thrown. Use the ground as a reference point, so y is equal to 0 meters, for measuring gravitational potential energy. So you can see down here in the image, this looks just like the image we just looked at, but I filled in the information that they gave us in the problem. So they told us that the maximum height was 4 meters. They told us the mass of our ball was 3 kilograms. And so I filled in the information that we know. We also know that at the top of the motion, our velocity is going to be equal to 0. We know that down here at ground level, as they told us in the problem, that our height is going to be equal to 0 meters. And so pre-lab practice problem number 1 wants to know what is the potential energy of the ball at ground level. So we know that potential energy is equal to m, so mass times gravity, g, times height, h, right? So at ground level, so at 0 meters, so that's this guy right here that I've highlighted, that's going to be equal to 3 kilograms, right? That's our mass, times gravity, 9.8 meters per second squared, times our height, which is 0 meters. So, of course, anything times 0 is 0, so we get that our potential energy at 0 meters is equal to 0 joules. All right, so moving on to pre-lab practice problem number 2. So same prompt up here. This time we want to know what is the potential energy of the ball at the highest point. So now this highlighted square is what we're looking at. We're looking at the highest point, so at H max. So once again, potential energy is equal to mass times gravity times height. So the potential energy at 4 meters is going to be equal to 3 kilograms, which is our mass, 9.8 meters per second squared, which is gravity, and 4 meters, which is our height, right? 4 meters is our height here. So when we multiply that out, we get that our potential energy at 4 meters is equal to 117.6 joules. All right, so moving on to pre-lab practice problem number 3. What is the kinetic energy of the ball at the highest point? So this is what we're looking at here. We're looking at the highest point, so where our velocity is equal to 0 meters per second, and also, of course, where our kinetic energy would be at a minimum. So kinetic energy, as we know from last week, is equal to 1/2 times the mass times the velocity squared. So the kinetic energy at 4 meters is equal to 1/2 times 3 kilograms, right? That's our mass, times 0 meters per second, because that's the velocity at 4 meters. And we're going to square that velocity. Well, anything times 0 is 0. So for the kinetic energy at 4 meters, we get 0 joules. All right, so moving on to practice problem number 4. What is the kinetic energy of the ball at ground level? So the thing that I really wanted to highlight here is that if the problem does not tell you that any energy was lost at the bounce, and if you look up here, you can see that nowhere in this problem, in this prompt, do they tell us that we've lost any energy. That means we can assume that potential energy, when it's at a maximum, is equal to kinetic energy at a maximum, which is essentially what we're looking for here, right? Because down here, kinetic energy would be at a maximum. That's where velocity would be at a maximum, right? So that's why it would be its maximum value there. Well, we know that it's going to be equivalent to what our maximum potential energy was. And thankfully, we already calculated that in problem number 2, right? So in problem number 2, we got that our maximum potential energy was 117.6 joules. So since we know that the maximum potential energy is equal to the maximum kinetic energy, well, we know that PE at 4 meters is equal to KE at 0 meters, right? Because this is PE max, this is KE max. So that means that KE at 0 meters is equal to 117.6 joules. All right, so moving on to pre-lab practice problem number 5. So still we're working with the same prompt, but this time we want to know what is the speed of the ball at ground level just after the throw. So you can see here, we're going to be calculating what the maximum velocity is, right? Because we're talking about the speed of the ball at ground level. But the important thing, and the reason that I emphasize the word speed, is you can see in the last step here, we're taking the square root. And you know, whenever you take the square root, you can have plus or minus, whatever that value is. So speed means that we're going to be taking the magnitude, so we want the positive value. All right, so the setup for this problem is, well, we know that the maximum kinetic energy is equal to 117.6 joules. So essentially what I have written here is that our maximum kinetic energy is equal to our kinetic energy at 0 meters, right? At ground level, that's where kinetic energy is at a maximum. So we know that where kinetic energy is at a maximum, this is going to be equal to 1/2 times the mass times the maximum velocity squared. So when we plug in our known values, we know that our maximum kinetic energy is 117.6 joules, and that's going to be equal to 1/2 times the 3 kilograms that our ball weighs, times our velocity max squared, which is what we're trying to solve for. So if you multiply 1/2 times 3, you get 1.5. And then if you divide both sides by 1.5, you'll get 78.4 on this side, and you'll get Vmax squared by itself on this side. So the last thing to do is to take the square root of both sides. So take the square root of 78.4, take the square root of Vmax squared. And this is what I mentioned in the beginning. You know, every time that you take the square root of something, you technically get plus or minus whatever that value is under the square root. And so this technically would be plus or minus 8.85, but because we want to know what the speed of the ball is, we're going to just take the positive value. So that's going to be 8.85 meters per second is equal to Vmax, or the speed in this case. All right, moving on to practice problem number 6. So on the way down, the ball loses 40% of its mechanical energy due to air resistance, though miraculously, there was no loss of mechanical energy on the way up. What is the speed of the ball as it returns to the ground? So the setup of this problem is almost exactly the same as the setup for the problem for pre-lab practice problem number 5. The only difference is this time we have an extra step in the beginning because we have to find out what 60% of the kinetic energy is, right? Because we lost 40%, which means we're left with 60%. So in order to find what Ke 60% is, we need to multiply Ke 100%, which is 117.6 joules, by 0.6. And so we get the kinetic energy, well, 60% of the kinetic energy is 70.56 joules. So now that we have what 60% of our kinetic energy is, we're just going to plug in our known values into this equation. So we have Ke 60%, we know that that's 70.56 joules. That's equal to 1/2 times our mass, which is 3 kilograms, times V 60%, so 60% of the velocity squared. So that's what we're going to be solving for. Once again, yes, we do want to solve for the speed of the ball, so that means at our last step here, when we take the square root, we're not looking for the -1, we're going to take the positive value, because remember, speed has magnitude, but not necessarily direction, right? It's a scalar quantity, not a vector quantity. All right, so we've got our known values plugged in. Once again, when you multiply 1/2 times 3, you get 1.5. If you divide both sides by 1.5, you're left with 47.04 on the left side of the equal sign, and then you're left with just V 60% squared on the right side of the equal sign. So the last thing we need to do is take the square root of both sides. So when we do that, we get that V 60% is equal to 6.86 meters per second. All right, so now we're going to change gears a little bit, and we're going to have a different prompt for pre-lab practice problems 7 and 8. So now we have a bead that's moving along a frictionless circular track with a radius of 3.5 meters, as shown in figure 5. I duplicated figure 5 here. So the speed of the bead at the lowest point A of the track is 5 meters per second. So what we want to know in pre-lab practice problem number 7 is what is the maximum height, so at B, attained by the bead above the lowest point of the track. So you can see in this picture, I filled in our given information. So they told us the speed of the ball at the lowest point A is equal to 5 meters per second. So you'll notice that I put that this is V max. That's because if you remember from our previous slides, down here at the bottom, this is where kinetic energy is at a maximum. So the same is true even on a circular track, right? At ground level, that's where our kinetic energy, or at point A, that is where our kinetic energy is going to be at a maximum. On the other hand, when our object is at its highest point, so at point B, that's where our potential energy is going to be at a maximum. And so the value that we're trying to find here is what H max is, right? We want to know what that maximum height attained is, and that's at point B. So I want to remind you of something from our first slide. So if the problem does not tell you energy was lost, you can assume it was not. Therefore, we know that PE max is equal to KE max. So that means that mass times gravity times the maximum height, which is what we're looking for, is equal to 1/2 times the mass times the maximum velocity squared, right? So as we talked about, there's mass on both sides, so those cancel out. So then we're just left with G times H max, the value that we're solving for, is equal to 1/2 times the maximum velocity squared. So if we rearrange the equation so that we're solving for H max, we're left with V max squared over 2G. So we plug in our known values. So we have V max is equal to 5 meters per second. We're going to square that. Then we're going to divide by 2 times gravity, so 2G. So 2 times 9.8 meters per second squared. And when that's all said and done, we get 1.28 meters. So now let's move on to the final problem, which is pre-lab practice problem number 8. So it says the center of the circular track is C, so this point here is the center of the circle. What is the angle ACB? So ACB, it wants to know what this angle is right here. So we know from the previous problem that this distance here from B to the ground, that's H max. So for simplicity, I just drew H max over here, but that's what we calculated in number 7. I think it's also safe to say that from C to A, this would be considered a radius, right? So we can say that this last little segment here between C and H max would be R minus H max, right? Because if this whole distance here is H max and the total distance is R, well, then this little segment here has to be R minus H max. That being said, I think we can all agree that this distance here from C to B is a radius, right? So they told us in the problem that the radius is equal to 3.5 meters, so we know that this distance from here to here is 3.5 meters. Now, because this right triangle is what we're going to be looking at to solve our problem, I blew it up and I just rewrote it and redrew it over here. Okay, so this is the same right triangle. We're solving for this angle here, theta. And we know that this side here, which would be our adjacent side, that's equal to R minus H max. Then this side here, which is opposite the right angle, that side is our hypotenuse. So we know our hypotenuse and we know our adjacent side. So it should come as no surprise that we're going to be working with cosine. Specifically in this case, we're going to be working with inverse cosine because we're trying to find theta. So we know that inverse cosine of the adjacent side divided by the hypotenuse is equal to theta. So now we're going to plug in our known values. So inverse cosine of r, 3.5 meters, minus h max, which we calculated in problem 7, 1.28 meters, divided by our hypotenuse, which is r, 3.5 meters. So when we calculate, we end up getting that our angle theta is equal to 50.6 degrees. So that's it for the pre-lab practice problems for lab 12. If you'd like to stay tuned, I'm going to do a review of collisions because as you know, there are going to be 5 questions on the quiz that pertain to collisions. And so I'm going to review that material now. So with collisions, we specifically focused on 2 quantities. Those were momentum and kinetic energy. So let's start out with momentum. So momentum, this is abbreviated as rho. You know, it is not density. So momentum is equal to the mass times the velocity. And with momentum, we know that momentum is always conserved. So that means that the momentum before the collision is always going to be equal to the momentum after the collision. Or in abbreviation, it's going to be rho I is equal to rho F, or rho initial is equal to rho final. Now, kinetic energy, on the other hand, is not always conserved. And the way that we find kinetic energy, which should be fresh in your mind because we were talking about kinetic energy today, but kinetic energy is 1/2 times the mass times the velocity squared. And if the kinetic energy is conserved, that means that the objects underwent a elastic collision, and that means that the kinetic energy before is equal to the kinetic energy after, right? Because no energy was lost in the collision. That's what energy conservation means, right? No loss of energy. However, in the real world, typically what we see is inelastic collisions, and this is where energy is not conserved, right? So this energy can be lost as heat, sound, friction, deformation of the objects. And what this means is that our kinetic energy before is not equal to our kinetic energy after, right? We're losing some energy in the collision, so our kinetic energy before is going to be greater than our kinetic energy after the collision. So just to really drive home my point about our types of collisions, we have 2 types of collisions. We have elastic, and elastic collision means that both momentum and kinetic energy are conserved. If we have an inelastic collision, this means that momentum is conserved, but kinetic energy is not conserved. Then we also talked about a specific type of inelastic collisions last week, and that was a perfectly inelastic collision. And this is a collision where momentum is conserved, right? We always conserve momentum, but because it's an inelastic collision, kinetic energy is not conserved. And what's special about a perfectly inelastic collision is that after the collision, the masses fuse together and they move together as one mass. So now let's look at this visually. Okay, so elastic versus inelastic collision. So before the collision, we have mass 1 traveling at v1 initial in the positive direction. Then we have mass 2 traveling at v2 initial in the negative direction. After the collision, both masses rebound off one another and change direction. So mass 1 is now traveling at V1 final in the negative direction, and mass 2 is traveling at V2 final in the positive direction. So as I mentioned before, we know that momentum is always conserved, so momentum is conserved in both elastic and inelastic collisions. However, we know that with an elastic collision, kinetic energy is also conserved. That means the kinetic energy before is equal to the kinetic energy after. So mathematically, what this looks like for this problem that we have illustrated up here, this would be 1 half m1 v1 initial squared plus 1 half m2 v2 initial squared is equal to 1 half m1 v1 final squared plus 1 half m2 v2 final squared. Now, if we have an inelastic collision, kinetic energy is not conserved. So that would mean that the kinetic energy before would not be equal to the kinetic energy after. However, if a problem asked you to solve for what the kinetic energy before is, this side of the equal sign shows you how to solve for what the kinetic energy would be before. And if it asks you to find the kinetic energy after the collision, this side of the equation would show you how to solve for the kinetic energy after the equation. But just remember, if it's an inelastic collision, these two quantities are not going to be equal to one another. Now, just to review perfectly inelastic collisions and what they look like. So I mentioned before a special type of inelastic collision, and that was a perfectly inelastic collision. So we know because it's an inelastic collision that energy is going to be lost. We know because momentum is always conserved that it's going to be conserved. But the special thing about a perfectly inelastic collision is that the masses are going to fuse together after the collision. So what that looks like visually is before the collision, you can see that we have M1, it's traveling at V1 initial in the positive direction, and then M2, totally a separate entity right now, is traveling at V2 initial in the negative direction. However, after the collision takes place, these masses fuse together, so we have one mass that's M1 plus M2, and they're moving together with one final velocity, V final. So what this looks like mathematically, since we know that momentum is conserved, we know that the momentum before is equal to the momentum after. So the momentum before is m1 v1 initial plus m2 v2 initial, and then the momentum after is equal to m1 plus m2 times v final. Now, because we know this is an inelastic collision, we know that our kinetic energy before is not going to be equal to our kinetic energy after. However, as I mentioned before, if we solve the left side of this equation, we would be finding the kinetic energy before. So if we wanted to find the kinetic energy before the collision takes place, it would be 1 half m1 v1 initial squared plus 1 half m2 v2 initial squared. Okay, if we wanted to find the kinetic energy after the collision, which of course is going to be less because we're going to lose some energy in the collision, that would be equal to 1 half m1 plus m2 times v final squared. All right, so that's it for the pre-lab practice problems for Lab 12 and the review of Lab 11. I hope you found this video helpful, and best of luck on Quiz 12.